So first part of the course, so let me just first go quickly over what the machine learning is, give you one tiny example of something, some old problem. And then after that, we're going to start with the clustering problem. So, I think in deep learning also we mentioned this stuff. So like what is machine learning? There are different definitions, like you can check Mitchell's definition, a study of computer algorithm that improve automatically through experience. So this is the way that Mitchell defined machine learning. Or, for example, Goodfellow says a form of applied statistics with increased emphasis on the use of computers to statistically estimate complicated functions, right? So you can come up with more definitions. Every textbook has its own definition. The reason is that there is no concrete definition for the term machine learning. But what I want to do, I want to explain you how practically it means that you're doing data-driven, computer algorithm for statistical understanding out of experiences. So this is the way that I define it. So machine learning is a kind of a set of data-driven approaches that help us understand the environment and its behavior and generalize it. So these are the main components that we need to do in machine learning. First of all, understand the environment, find out what is its behavior, and this understanding should be able to generalize. And then through a semester with different sort of examples in machine learning, you're going to get this idea. What do we mean about every single of them? So first of all, what is data-driven approach? And like data-driven approach, the name is on it. So you basically talk about everything based on looking on a bunch of data. So you do not do any analysis or something like that. And the very well-known example is Ohm's law. Do you know about Ohm's law? I mean, definitely, right? So you're an ECE guy, and you do know what is Ohm's law, right? What is it? Electric current, right? Related to voltage, right? Do you know the equation? What is it? Don't laugh, just tell me, because that is machine learning, right? Yeah. V equals by Ri, right? V is the voltage equals by R times I. This is the electric current, right? And this R, what is it? Resistance, right? What is the unit of this guy? Ohm. And this is just named after this guy, right? Yeah, he did it on 1827. And do you know about the proof of Ohm's law? Do you know about that? Who knows about the proof of Ohm's law? There is no proof for that because it's a data-driven law, right? So what did Ohm do? Do you know what he did? So he was a professor at that point of time, and he had a lab, and he did this experiment. So he put like resistance, like Cooper, I guess, Cooper plates, and then he could change it based on the thickness and the length of the different plates. And based on that, each time he had the galvanometer, so he could compute the or measure the currency. The current, electric current out of it. And then he was changing the voltage. He was looking at the current for different components, right? And then he got different points. So he just plotted this curve. He said that I do have a curve. And then here is, for example, voltage. And then here is the electric current, right? So I just put the voltage in something. The electric current happened. Then another point, you just take it. Another point, you take it, and so on. And then after that, you say, like, I guess they are related linearly. And actually, there is no proof that they are related linearly. You cannot prove it, right? So you can approximate it linearly nowadays, we could say. But at that point of time, he didn't think about that, right? And he had this guy. And he just noted that there is one line passing through the center, and that line is the slope of that line is changing when the material is changing, right? and he called it the resistance of that material. That was the way he did it. He actually had another law, which was about the acoustic waves, and he did it the same way. He basically did some experiments, and he started to talk about the range of the wave, I guess, based on the initial like force you impose to the, the speaker or the wave generator. And then that law turned out to be totally false. I mean, he did experiments. He ended up having some curves and some theory on, not theory, but some law for that, but then it turned out to be false. And this is why you have not heard of this, right? You say Ohm's law, you just simply think about this law, right? Whereas there is another law, you're not knowing this, right? So this is data-driven approach. So Ohm did not have any proof or any theory that he could say that electrical current is going to linearly scale with the voltage, with resistance coefficient. He did not have this. He just did some sampling, collected some data, and based on that, he came out with some sort of rule. This is what we call it data-driven. So what he did, he basically started to see some pattern. Definitely, Ohm did not wake up one morning and say that I'm going to do this experiment, right? Probably he was doing this for quite some time in the lab, and he started to see that when he changes the material, this change of the measured electrical current is going to behave differently. And he was starting to hypothesize this kind of hypothesis that, well, if I increase the material I have here, which makes more resistance to everything, then the electrical current is going to drop, right? He wanted to validate this hypothesis. He had no way but doing the experiments, so he collected some data, right? The one which I showed you on the board, and out of that, he concluded some sort of pattern, right? The pattern is that the electrical current is going to linearly change by voltage, and the slope of this linear change is proportional to the material that you have there, right? So this is the idea of data-driven, and you can do it for many things, right? For example, thermodynamics, initial version or initial laws in thermodynamics, they were totally out of experiments, right? So people go in the lab, check volume, and compare it to the temperature and pressure, and then they started to see that there is a kind of pattern. Like you change one of them, the other guys are going to get impacted, right? And they tried to somehow capture these pattern by some mathematical formulas. But they were not exactly coming out of any theory, right? Simply out of the experiments they did, right? Now, these are the three things that you have in machine learning. And what we do, it's quite hard when we talk about the general machine learning to put label on every single of them. But I just give you a very general understanding of these things. And then we start with the very simple problem of clustering. And gradually we get into the other topic, problems, which give us more clear idea about that. So the first thing is model. So what is the model? It's basically something that is going to describe the pattern you see in the data, right? So the model that Ohm considered here was a simple linear model passing through the origin, right? He said okay, I assume that the voltage and electrical current are linearly connected, right? But he could have considered much more complicated one, right? The summation of lots of exponential functions, right? That one could also move like this, right? Something like that, right? You could have considered this one. Obviously, with the computational power he had at that point of time, it doesn't make sense to do this, but he could do that, right? And if he would have done this and ended up with some law, maybe we were still using it, and we call that one Ohm's law, right? Who knows, right? So that is the model, something that is capturing the pattern, right? The model obviously needs to capture that pattern. It means that something that we see, if we increase the voltage, the electrical current should go up, right? You cannot consider a function where the voltage, for example, drops with the current, right? That is obviously not capturing the pattern, right? But any function going up and somehow going monotonically up with no bound at the very end, then it might sound reasonable, right? Any function of that form. This is what we call it model. The second component is obviously data. This is the one which you get out of experiments. You do lots of experiments, and you get data. And then the last thing is the learning algorithm. And what is the learning algorithm? The learning algorithm is the one which looks at the data, and then it goes back to the function that you considered, and it somehow modifies the function in a way that this function is perfectly matching the pattern you see. Maybe not perfectly, but at least approximately. What does it mean? It means that maybe Ohm considered here that I have a linear function, right? But how does this linear function look like? Does it pass through the origin? Does it have any offset? Or, for instance, how does this line and this slope depends on the material that you use, right? So this is something that you do not have it inside the model. The model simply says there is a line going up, and that line is going to describe the connection between voltage and current, right? And then the question is that how I can find the slope of this line, how do I know what is the offset, right? And then this was the learning algorithm that Ohm used to get those parameters out. And he basically just did lots of experiments, and if you check online, you can see his handwritten notes where he tried so hard to find out what is that slope, right? And he called it, this is resistance, right? So that is the learning algorithm that you do, right? So it's a kind of algorithm or a mathematical process that you start from data, you try to find out what is the best choice of the model. Now, we could have different sort of examples in our world where we have these kind of problems. So the first one, which we hopefully start with today, is the problem of clustering. And what is clustering? Well, you have data samples like this guy, these points here, and these data samples are scattered all over this space. For instance, here in this example, I have these data samples, and these are two-dimensional samples. So what they are showing monthly amount of transactions. How many transactions? Why? So these are collected from bank accounts. So you go on in one bank branch, and now for every single bank account, you check how many transactions this account is doing in 1 month. Okay? This is one of the components that you have in your data. The other one that you have is the monthly amount and monthly number of transactions. So for every single account, you're going to see how many transactions are being done and how many transactions are being done. For example, one account, you see that in the last month, it has done only few transactions here, as you can see. Maybe, so many transactions. So it's here, yeah? So this is the number of transactions, and maybe it is, I don't know, 20, right? It has done 20 transactions, and then the amount of transactions altogether, maybe there are $1,000, right? So there is $1,000 of transactions, right? This is one point that you get, right? Now, you can do it for every single account, right? You go for the next account, it shows up here. Next account, it shows up here, and so on. And there are also some accounts here. For example, this is just, I don't know, 2. And the amount is much larger, like, I don't know, 8,000, right? Something like this, right? Now, you start to collect those data, and you're going to look at this one. So you see that the points that you have collected look like this. So every single point that you see, for the moment, ignore the yellow points, but blue points, blue squares, and red triangles, all of them are points you collected from the bank branch, right? And now, you look at this data, you start to see a pattern. What you see? You see that there are people who are just transferring a few number of transactions, They are the rich people, for example, right? And these people, they do just a few transactions, but the amount is significantly high, right? Because they are rich, they don't care about every transaction they do, right? Just 2 transactions, each of them 4,000, that's it, right? But there are a bunch of other people, like me, who are doing lots of transactions, but each of them are $10, $15, $50, right? So people are usually within these 2 scopes, right? Some people use their account for major transactions, few times per month. Some people use their account for their daily costs, right? A lot of transaction, small amounts. But what if now you start to see some point here? This guy is transmitting lots of transactions with a lot of money being spent, right? This might sound a bit weird, right? Maybe it's fishy. Maybe it's a kind of fraud account. Maybe they are doing some sort of illegal actions, right? You might tell the bank, right, it does not fit into the pattern, right? And this is the kind of problem, kind of thing sounds totally like logical for you, right? This is the problem that we consider in clustering, and it's again understanding a pattern out of data, right? So I look at the data. I did not know initially that the accounts are somehow being roughly clustered into these 2 parts, right? I had to look at the data. After looking at that, after looking into so many bank accounts, I started to see this fact, right? So here is the kind of pattern I see. Maybe I use a model. We're going to do this later. I make a model that describes this, so it means that any new sample I give to this model, it's going to give me 1 cluster, and it's going to tell me with this whether it is a very well-populated cluster or is a small cluster with few components in it, few samples in it. Then I collect it out, I understand it out of the data that I see. So this is the learning process that I am doing, right? Everybody's clear? So now that I understand this, then if I see a point like this, this is going to help me do some argument about that point, right? Whether this point, this new bank account sounds normal or it sounds a bit fishy, and I should take more look into it, right? So this is the problem of clustering. Another problem that we are going to discuss is the problem of classification. What is the classification? Well, look at this chart here again, this diagram. So I have this these points, and they are collected for many samples. So I am going to some pet store, whatever, and then I start to, this pet store has cats and dogs, right? And then I take a look at every single pet, and for that one, I start to just collect 2 parameters. One of them is the sleep time, how many hours the pet sleeps, and the second one is the number of times the pet makes noise during the day, right? And I start to somehow plot that, right? So what I do, for example, I see one cat, and the cat is doing like, so here's the sleep hour. I don't know, it's sleeping 12 hours in a day, right? And then the number of times it gives me a sound or makes a noise is, I don't know, 5 times, right? So this is some sort of point here, right? And I do know that this is a cat, so I'm going to write a cat on top of it, right? And now the cat I see is sleeping roughly the same amount, but it makes 6 times noise, right? So I again write it down, cat, right? And now I also look at some dogs, so I see this dog is just sleeping, I don't know, 5 hours, for example, and then it's making too much noise, like, I don't know, 20 times it's barking, right? So, and I write on top of it that it's a dog, right? And some other points maybe, like this, and so on, right? Now, the point here is that after collecting this data, I start to see that there is actually one nice curve, right? And if I draw this curve, any cat is happening on one side of the curve, and any dog is happening on the other side of the curve, right? So what I could conclude, I could say, well, it means that if I know what is the sleep time plus the number of times that it makes noise, I can say what is that pet, right? This is the problem of classification. It means that looking at the data, which is related to the cat or dog, but is not specifically telling me it's cat or dog, right? Looking at that data, I want to decide whether it's a cat or dog, right? For example, I just want to know what is the pet of my neighbor. I'll listen how many hours it sounds like sleeping, how many times it makes noise, and then out of that I conclude. I mean, I should be very stupid because out of the noise you can find out what is the pet, right? But say I am a very nerd guy. I don't care about that. I want to use machine learning, right? And then it's a kind of classifier. So I can draw this curve, for example, and I would say any point happening here is a cat, any point happening here is a dog, and now you tell me how many hours one pet is sleeping, how many times it makes noise, and then I can tell you what is that pet, right? Clear? This is a classification problem. Again, you're doing the same thing, right? You're collecting data. You're modeling it. What is your model? You would say there is one curve which is distinguishing between the pets, right? So you have seen the pattern. You make this model. You collect data. And out of that, you try to understand what is that curve, right? Whether it's a straight line, whether it's an exponential curve, or anything like that, right? Everybody's cool? OK. This is the problem of classification, for example. Problem of regression. Again, you do have relation between two things. We are going to, again, discuss this one. For instance, salary versus the years of experience, right? You want to see, like, if I'm working right now is I don't know how many years, and then I want to know how much I'm going to get paid in 20 years, right? You want to predict this. So how you can do this? Well, you might say, OK, it makes sense that if I keep working, I'm going to get more and more, supposedly. And then the second thing is that I cannot simply go up forever, right? So there is always a sort of saturation. The more experience I get, the smaller going to be the increase, right? And maybe there is a kind of, saturating, upgoing function relating these two things together. Now what I'm going to do, I go ahead and ask my older colleagues, how many years of experience you have, how much you get paid, right? And then I make those points, right? And then I try to fit a curve which is matching these points, right? Now, out of that, I start to see what's going to be if I start working from now for 20 years, right? Then I'm going to have this much of experience. So roughly speaking, I'm going to get paid that much, right? This is the problem of regression. It's, again, based on the fact that you see in the data, you look at everybody, you see everybody going to get increase in the payment through time. Based on that, you understand this pattern. Now you collect data. You try to somehow fit a model into this data. And this one is going to give you a rough idea what's going to be the exact or the payment you're going to get in future, right? Questions? Everybody's clear? So this is the problem of regression, which we are going to, again, cover in the second part of the course. And another problem is the problem of playing chess, right, or playing any game board. So now this guy is a bit of a more complicated problem, but again, is a learning problem. And what is happening here is that you got an agent, one guy, you, who is playing the chess, and you got an environment, which is the chessboard, and the other side who is playing, right? Now, what you're doing, you're going to do one move, right? So you move a piece, right? And then the environment starts to act, to react to what you have done. The other side also moves a piece, right? Now, every time that you do an action, every time that you move, the environment changes the stage, right? The whole game changes because the other side also moves, right? And out of that, you get a reward. For example, you're an experienced player, and you see that, well, that was a bad move, right? So you get some understanding, right? And out of that, you start to build your next action, right? Now, when you keep on playing with someone, probably the first move is to just measure how expert the other side is, right? And what is the strategy that the other side is playing with, right? Now, you cannot say it for sure, but you can somehow, if you play enough, then you start to get idea, right? This is the way, I mean, this form of playing, right? So I probably should be careful about this and that, right? And this is going to build your policy, right? Your move, your next move, every time that you see the environment. Again, here, the whole story is the same thing, right? The whole story is that you're seeing a pattern. The pattern is that, for instance, the other side is an experienced player, and then you keep on collecting data to find out what is probably the strategy of the other side. And based on those data, you learn how to play, right? And this is the learning algorithm that you do. This is the topic that we cover in reinforcement learning. As I told you, this is somehow out of the scope of most classical machine learning topics. It is a part of machine learning in general, but this is a kind of, singular sibling of all other topics in machine learning. So this is something that we discuss in other courses, not here, but I just want to give you some understanding. And once we are over with the course, in a short final presentation, I'm going to give you the main idea in reinforcement learning and what are the ways that you can do it and how you can use like deep learning, for instance, or other forms of machine learning into that. So everybody's clear? Any questions? No question? Great. So if you got no question, so I hope that this help you to just understand what kind of problem you're dealing with, and gradually, as we progress in the course, you get more and more precise in your definitions. Now, let's start with the first component, data. So what is a data set? Data set, the name is on it, right? A set of data samples, right? So it's a set of different samples, axes. For example, these axes could be the one which we had here, cats and dogs, right? So the X is telling you the number of hours it slept, the number of times it made noise, and the kind of pet that you have, right? This is the data set. Or for example, here, the data set is the amount of payment, the number of payments per month, right? Every single point is like this, right? So here, the data set includes points which are two-dimensional. In that one, it includes points which are three-dimensional, right? Hours, hours, number of times it made noise, and the type of the pet, right? So, but any data set can be always shown in this form. Now, you can try to think about clustering, classification, regression, playing chess, all of them that we have, right? So, for example, in the clustering one, in this guy, right? These are the samples, right? And all of them together just make the data set, right? So you go to the bank, you make all of those samples, you just write it down in a spreadsheet, for example, and then that one is your data set, right? Or, for example, in the classification, this guy, so you just go to the pet store, you make that Excel sheet with 3 different entries for every row, and that guy is going to be your data set, right? And so on for regression and also for playing chess. So now, what about the model? What does the model do? Now, the model is usually looking at the kind of data that you have, right? And this is a bit tricky to define it exactly here. This is why I'm just giving a very generic definition here. But once we get into every single learning task that we have, every single topic that we're covering, we're defining exactly what is the model there. So the model at the end of the day is a function which is looking at the data that you have. This data could be the data that you have seen before, the one existing in your data set, right? Or it might be a new data, right? It's going to look at that one, and it's going to give you some output. And that output is somehow explaining the pattern that you are looking for, right? So the easiest way that you can think about this is the classification problem, right? So here you can simply say what is the output, because basically your problem is supervised, and you can simply define a label, right? the input that you are going to give to your model is going to be this number of hours and number of times it barks, right? And then, as the output, you're going to get the label, whether it's a cat or dog, right? For example, in the regression problem that I told you, the input you give is the number of years one person has worked. The output you're going to get is going to be the amount of money they get paid, right? But for the clustering problem, for example, that is a bit more complicated, right? So can you tell me what is the output in the clustering problem? What is the input? What is the output to the model? Any idea? Right, the label of the cluster, right? But you do not necessarily have poor and rich. I mean, in this example, you have the poor. It depends how many clusters you want, right? You look at the data, and then you decide, for example, to cluster it into 5 clusters or 2 clusters. It's your choice. But at the end of the day, it's going to tell you, OK, this is the cluster of a new data you give, right? That's right. Everybody's clear about that? So this means that, for example, in this example, if you decide to have 2 clusters, we're going to see it later, hopefully today. So if you want to know, the data that you give to your model is the number of transactions and the amount of transaction. And the thing that you get at the output is, for example, the cluster of the data, right? This is one thing you could get, right? Or, for example, it's going to tell you whether it fits into the normal distribution of the data or it's out of the normal distribution, right? This is another thing that you can get out of clustering. And again, as I said, it's a bit hard to just see it immediately here or give a general definition of the model. But as we get into the problem, for every single problem, you can specifically define it, so there's no problem there. Everybody's cool? So you can think about whatever we had before, clustering, classification, regression, or even playing chess, right? What about the playing chess? Do you know what is the model? It's going to look at the other guy's play, right? Looks at the chessboard, and then out of this, it decides for the next action, right? This is the model, right? Takes as the input the situation that the game is in, and then as the output, it's going to tell you what is your next move, right? It's a model, right? This is what we call it policy in reinforcement learning. OK, now, what about the learning algorithm? So learning algorithm is easy to define, right? It's going to look at the data set, all of the samples that you collected. It's going to find you a very good model, right? F a star. This is what I show by F a star. Now, you might tell me, what do you mean by F a star? You told us that this model itself is a function. Now, what is F a star doing here? Well, if, for instance, I assume that in the Ohm's law, if I assume that my voltage is increasing by electrical current linearly, that line could be any line, right? It could be a straight line passing through a region. It could have offset. It could be any line, right? The line could even go down, right? But then I look at the data, and out of the data, I conclude this line is a line which is passing, among all the lines possible, is the line which is passing through the region. It's proportional, its slope is proportional to the resistance of the material, right? Everybody's clear? So now, among all the lines available which are fitting to the model that I assumed, is actually the line, this is the one which is best fitting to my data, right? And how I find it out, this is the learning algorithm. Again, for every single specific problem, the learning algorithm is a bit different to define. But at the end of the day, gradually you're going to see, you always try to define an objective, or what we call it a loss function. It's not really a loss function, but it's a kind of measure of distortion. It's going to be exactly loss when you just think about basic supervised learning problems. But it's a kind of measure of distortion or metric objective, and then you try to optimize that objective. This is why machine learning is very involved with function optimization. And this is why gradient descent is the most popular algorithm in machine learning. Now, because at the end of the day, you want to solve an optimization problem. But typically, this optimal function, this means that the function among all things that you can have, the one which is best fitting your data. Now, again, you can think about these different examples we had, and you can try to formulate the optimal function there and the whole learning process. For instance, in the playing chess, the learning process is the process that you look at every single move of the guy playing with you and the status of the chessboard, and out of that you find out what is the best strategy to play, right? This is the learning algorithm. But as I said, for every single task, you can formulate it a bit differently, and we're going to do it through semester, so you're going to get very happy with that. Okay, so now this question remains still. I mean, I tried a bit to explain what is a good function, what is a good model to choose, but we're going to get there gradually. Questions? Okay. So if you got no questions, then let's start with the unsupervised learning part. Basically, we want to just start with the clustering. So what is the idea in the clustering or unsupervised learning? In unsupervised learning, actually, we don't have any label for the data. This is why we call it unsupervised. It means that every single sample that we have inside this data set, it does not have a label. It doesn't say it's a cat or dog, right? It simply says, like the clustering problem we report, it just tells us what is the number of transactions and amount of transaction, right? And there is no label for every single account. Nobody told you that this is the account of a poor guy and this is the account of a rich guy, right? You came up with these theories, right? This is on you who calls people rich or poor, right? So there is no label. You don't label anyone, right? Okay, great. So that is unsupervised learning. So basically the model, what it does here, it captures the pattern hidden inside the data. For example, it tells that the data is actually looking like a Gaussian distribution, clustered into two different Gaussian bells, and each of them is happening here and there, right? This is something that we're going to do in clustering, right? And the learning algorithm basically looks at that data, and then it tries to find out that pattern, the best way that you can describe this pattern. So there are three major things that we're going to do in this part of the course. The first one is the clustering, which we start today. And after that, we're going to get into the dimensionality reduction. That is basically PCA. And then this gives you the idea that, for instance, if you have a data, then again, I mean, the data is high dimensional, then you want to represent it in a very smaller form. And how you can do it, there is, again, no label, right? For one high-dimensional data, there is no labeled low-dimensional data, right? You can give different forms of compression, and among them, you want to choose the best one, right? This is, again, unsupervised learning problem and distribution learning, right? This is, say, the kind of most general problem in the whole machine learning. Basically, you can say any problem, to some extent, somehow lies within the scope of this problem. This means that you look at data, and the data samples are different. Some of them are happening too much, some of them happening not too much. And then out of that, you want to come up with one distribution function, which is somehow describing this data, like giving you the statistics of that data, right? And I'm going to show you that if you can do this, then you can generate data. This is what diffusion model does. This is what ChatGPT does, right? It just learns the distribution of the language, and it starts to generate meaningful sentences, right? That's the way you do in generative AI. So we start with the clustering today. Just as a short note, here we could have labeled data. This is basically, for instance, this is here, right? For every single point, I give a label, right? I say it's a cat or dog, right? Or for example, in the regression problem, I give you, for every single number of years, I give one specific amount, right? This is the amount of payment, right? So the data could be labeled, and then the whole learning process is that you know what is the label of a new data which has no label, right? It might sound like this is different from the previous one, but it is literally not, right? Because this is the extreme case of the previous one. Like the previous one is the more general one. But we're going to get there, no worries. Just wanted to give you this hint before ahead. We leave it for now. We get back there quite later. And then the key point here, as I told you, the key things that the model does is to just find out what is the relation between the label that you have and the original data. And the learning algorithm basically finds the best model which somehow represent this relation. Classification and regression, they are the famous tasks within the scope of supervised learning. Okay? And we're going to talk about them later. Okay, cool. Now, one last hint on the reinforcement learning. I just wanted to give you this hint that actually data that you have inside unsupervised or supervised learning is hardly describing exactly what is happening inside reinforcement learning. Usually in reinforcement learning, you have that kind of data. And that kind of data is that, like you have A, this is the action that you do, or the agent does. This is the state that you're in. This is the reward that you get, right? This is one single point on a trajectory. And you have a long trajectory. You start playing chess, you do one action, you get into a state, and then you get one reward. You do the next one, next one, next one, next one, next one. Oops, the game is over, right? You won. This is one trajectory. You can again start playing, right? You keep playing, again, you lose this time, right? It's another trajectory, and you keep on going, right? This is the kind of data set that you get, right? So the ultimate thing that you want to do is that if you start playing once, right, the rewards that you keep on getting is higher, are maximized, right? Meaning that, like, if you play chess, you win, and you win very fast, for example, right? So this is the return that you get, and you want to maximize that return. So the model, in this case, typically describes the policy. It could describe also the value, but this is not something that you need to worry about right now. But it basically what it does, it just describes the way that you play the chess, right? You look at whatever you had before in your trajectory up to this point, and now you decide what is your next action, right? This is the model, for instance. And then the learning algorithm is that it looks at this set, which is your experience before, whatever you have played, and out of that, it tries to find out what is the best move, what is the best policy, right? So this RL is, as I told you, quite away from classical machine learning. Like most things we have in machine learning, you can somehow get very fast into that because the framework is very well matched with the general, say, supervised, unsupervised learning framework. But for RL, this is quite different. And it's a bit harder in terms of making it work. And it's a bit more, say, older because it happens everywhere in any control problem. I'm going to give you a brief introduction at the end of the semester, but we have a separate reinforcement learning course. Actually, we have a couple of them in UofT, but we have one RL, deep RL here at ECE as well. Okay, so that was it regarding the introduction. Any questions you might have up to this point? Yeah? This one is time. Like this is the first time step, second time step, and so on, right? Any other question? No question? Okay, so if you got no question, you can check into Bishop. This is the original, the main textbook, as I told you. Tibshirani's book, you can ESL, you can take a look. These are the other things. I mean, I would say that Bishop is the best one if you want to take a look and just get a bit of reading on the introduction. Okay, so then, if you got no question, let me start with clustering. I don't think that I can manage to finish it up, but I just give you the first idea, like let's say what is clustering and how we can just develop one very simple algorithm that is actually doing the clustering for us. So the first question you might ask me is that why you were starting with unsupervised, because there are lots of lectures all across the world on machine learning, and everybody starts with linear regression, right? And why you do not start with linear regression? The first thing is because I can. But the second thing is that like it makes more sense to me to start with unsupervised learning, because the supervised learning problem is actually a special case of this one. This is one point. And there are lots of things involved here, like many linear algebra background you need, that you might need, or probability theory that we can't cover here. So when you get into that part, you don't really get any confusion anymore. This was the idea by one of our colleagues, that we start with unsupervised learning. We have tried it a couple of times and with different approaches, and it somehow proved us that this is the better approach. So it's not out of laziness. It really, we have put thought on it. Okay, now we start with the problem of clustering. Problem of clustering, as Sir David McKay says in his book, is that this is one of the most basic problems of intelligence. So basically, we as intelligent creatures, we started to somehow become intelligent by doing clusterings, right? So probably the first, people of decision, or creatures of decision making on Earth, were not really having too much of clusters, right? Then they started to somehow make different clusters, like these things which look like, long, and then it has like some leaves on it. It's a tree, right? And then those which are looking the same, but they are smaller, we're going to call them flowers, right? Who can define a flower? I mean, I do know you can define it nowadays, but again, this is a clustering, right? I guess for a very child, flower and tree is in the same cluster, right? And gradually they start to distinguish between them. And as you get more and more intelligent, you do more and more clustering, right? So, for example, you say, we have plants, we have animals, I don't know. Then within plants, it's like trees, flowers, other things, right? So animals, again, there are different forms of animals. And then if you get into much more specialized person, then they're going to tell you, okay, the trees themselves have different form of families, right? And within those families, there are, again, different subfamilies, and so on, and so on, and so on, right? So I think that guy is definitely much more intelligent than me within the scope of trees, right? And this is why they know like much more details and clusters there, right? So clustering itself is a sort of basic action that any intelligent creature does. And the more we do it, the better we get intelligent. As the time is passing, we feel like as human beings, we are getting more intelligent. And this is basically because we get more deep into things and try to find out the distinguish between different parts of it, right? So this is why, for example, McKay considered this one as a very basic problem of intelligence. But philosophical story aside, what is the main problem here? So the main problem that you have a bunch of samples, right? And these samples are collected. They are the bank account information that I told you in the example. You have collected them inside one set, which is your data set. Now, what I'm going to do from now on, whenever I want to visualize things, I always think of these axes to be two-dimensional. The main reason is that I can show it on the board, right? But you do not really need to think only about two-dimensional thing, right? So this makes sense. Every single of these guys is one of the samples inside the data set. That is correct. But your data sample could have much more features in it, right? So you don't simply take the monthly payment and the number of payments. You also take the kind of account, like it is saving, checking, or something else, right? You get like the day that it was opened, right? You get this monthly payment of the monthly income of the account owner, right? You can add more to it, right? And then it's going to get longer. So this X could be very long vector. Now, the thing that we want to do, we want to look at this data and come up with a clustering. And clustering in general, it does not have any specific rule, as I said. Like there is nothing telling you that definitely this account is rich, this account is poor, right? This is a kind of naming you are giving to it. And you even don't know how many clusters you have, right? Maybe bank accounts are looking like this, like they're getting roughly clustered into 2 clusters. Maybe there are more clusters, right? Maybe there is 1 cluster here as well, right? And then it depends on you. Maybe you would say that, okay, these guys are 1 cluster, these guys are 1 cluster, and this guy is another cluster. Maybe this is your decision. Or maybe you say that, no, I would like to cluster it this way. I would like to say that everybody here is 1 cluster, and everybody here is another cluster, right? So there is no predefined label for anything, right? This is your choice. You choose to just cluster it into 2 different clusters. And how we define every single cluster is, again, your choice, right? And this is basically the model, right? The model is the one which looks at one part of this page and tells you it belongs to which cluster and how many of them you have, right? So the model that you have is some function of this form. So for example, you agree that, okay, I would say I have k different clusters, right? I have 10 clusters. And now I want to have a model, and this model is looking at one sample, and it tells me it belongs to which cluster, or it better fits into which cluster, right? Everybody's clear? So your function is going to take one x and is going to give you one cluster. And this cluster is, again, among multiple clusters. How many clusters you have, this is what you choose. How you just do this mapping, again, this is what you choose, right? And among all of these possible mappings, which are infinite number of them, you want to choose the one which somehow makes more sense, right? Everybody's cool? Okay, so now if you consider one particular clustering model, so if you consider one thing that is looking like one function which is taking k, and then it's going to give you the cluster of every single point, then what you could say that if I look at every single point in this space, which is a data point, right? This point is a potential data point. Maybe this guy is inside your data set, maybe it is not, you don't care, right? So there could be one guy with this number of payments, I don't know, 3, and this amount, which is, I don't know, $1,326, right? There could be one guy. Maybe you see it in your data set, maybe you don't, right? You don't care. This is one point, which I call it x, right? And now, every single x, when it goes to that function, it's going to get into one cluster, right? It gets belong to one cluster, right? Now, if I get every single point in this space, each of them has its own cluster, right? What I can say there are a bunch of points, for example, here. They all belong to the first cluster, right? Cluster 1. Any point here is going to belong to cluster 1, right? Everybody's cool? Now, any point in this part of the plane, any point here, it belongs to cluster 2, right? Not 8, 2. Right? Anyone here belongs to cluster 3, and so on, right? So you could define one cluster subset in your space. So you would say, I can have any point. For example, I can have any number of transactions, right? And I can have any amount, right? And they all are positive. They both are positive, obviously. But that's it, right? And now any point in that space belongs to one cluster. Now, the cluster subspace is the set of the points which belong to the same cluster. Clear? Now, if you collect all of these clusters, if you just take the union of all of them, you just combine all of these clusters, this is obviously telling you the whole space that you have, right? Because any point belongs to one of the clusters, right? And most of the times, the clustering that you do is that one point cannot belong to 2 clusters, right? It's either poor or rich, right? You don't put anyone in between. Or it's at the same time poor and rich, right? But we can do it. We actually could say that this guy is with probability 60% poor, 40% rich, right? We can do it as well. But it is not something that we are doing right now. We do it later. Okay? So this is the kind of properties you want the model is going to do to your data space, right? It's going to look at all possible data that you have. It's going to cluster each group of them into one cluster. These clusters together are going to say what is the whole space that you have, and then the clusters are not overlapping, right? Everybody's cool? Okay, now the question is that you do not have access to every single point, right? Clear? You cannot go ahead and just collect information on all bank accounts on the planet Earth, right? And even if you have access to that, who knows? Maybe there are aliens, right? You don't have access to their account, right? You cannot collect all the information, right? What you get is the information of some bank accounts, right? So you're going to get access to a data set which is not covering all the points here, right? Some points. And then what you want to do out of that, you want to somehow come up with this idea that, okay, my data is going to be clustered into, for example, 2 clusters. And every cluster, if I see a new point, I can find out which cluster it belongs to, right? So this is the learning algorithm that you want to do. So your learning algorithm is looking at the samples that you have collected, and it's going to tell you how does every single cluster set or cluster subset that you have, these guys, how does every single of them look like, right? It also tells you how many of them you need, right? What is K? I'm going to tell you as well. So this is the learning algorithm, and you are looking for a good one. And then again, the question is, what do we mean by a good one, right? So a good one means that, like, it makes sense, right? But then I'm going to formulate next session what is exactly a good clustering algorithm, right? You can define it mathematically. Okay, now let me start with the k-means clustering. This is going to be the last thing we have today, and I'm going to just give you the algorithm. I'm not explaining how we ended up having this algorithm, but I guess this algorithm is going to make sense to you, okay? Once you understood this, then we try to formulate this algorithm. We again get back to the problem, and this time we try to somehow define what is a good way of doing clustering, right? And then we see that this algorithm is actually solving that mathematical problem, and this algorithm makes sense to you, okay? Maybe this somehow helps you that what you see intuitively is basically what you are doing at the end of the day, okay? Now, what I'm going to do for the clustering, I'm going to decide on k different clusters, right? I would say, okay, I want to have 5 clusters, for example, right? And now what I do for every single cluster, so let's do it for 2 clusters. Okay. Let's do it for 2 clusters. Say that I want to have 2 clusters. And for these 2 clusters, I'm going to consider, 2 centroids. I'm going to consider mu1 and mu2. Okay? These are the centroids. One of them is for cluster 1. The other one is for cluster 2, mu1 and mu2. Now, if I get a new point in this space, so this is the point x, what I'm going to do, I'm going to check the distance between x and this centroid and the distance between x and this centroid. And it's going to belong to the cluster of the centroid, which is closer. Does it make sense? Everybody's clear what I'm doing? So k different centroids, mu1 to mu k. For every single point x that I have, I'm going to check the distance between x and every single centroid. And then the centroid, which is the closest, is going to represent the cluster at that point, right? Makes sense, right? Yes?
Is k means the same thing as k?
Oh, no. K nearest neighbor. No, it's not the same thing. That is for classification, actually. Okay. Yeah, but it's okay. Yeah, you get the k nearest neighbors, and then you take the majority vote. If this is the one you think of, yeah, that is a different thing. Yeah. Okay. Everybody's clear? Okay. Now, Here, for instance, I have these points. Maybe my clusters are here, here, and here. Now, these points on the lower part are closer to this one, so they're going to belong to the red cluster. The one on the left belongs to the right, green cluster, and the one on the right belongs to the blue cluster, right? It makes sense, right? This is the thing that you're probably intuitively think about clustering, right? If you have data, probably those who are close to each other, then they are going to belong to the same cluster, right? Okay, now the thing here is that this guy is what you have as your clustering model. So this is your clustering model. Now inside this clustering model, can you tell me what is the thing that you can freely choose? Mu, exactly. What else? K, right. K and those centroids, mu, are the things that you can freely choose, right? So I can change my model by changing the centroids, right? If I put the centroids here, now this guy is going to get clustered by this one. But if I move this centroid here, now X is going to belong to the first cluster, right? So by changing the value of mu, then the cluster is going to change. So this guy is the model that I have, and the parameter inside this model that I can freely change are K and the centroids, right? Everybody's cool? Okay. Now, this could work for any number of centroids, so I can just cluster it in 3 clusters. I can do it more, I can do it less. And yeah, any point that I have in the space, it can be clustered. Now, the question is that what is the best choice of these mu's, right? Now, it's getting a bit more clear what do I mean by a good model, right? So I mean what is the best choice of the centroid and K, right? But again, how do you define the goodness here, right? This is something we're going to do next session. But basically what I want to do, I want to start from a few samples that I have collected, and based on them, I decide the number of clusters, K, and also the centroid for every cluster, right? Somehow that these centroids make sense, right? Everybody's cool? What we're doing? Okay, now, let's just do k-means clustering. It's quite intuitive, and then we'll later understand why we did that. So, the first thing that I'm going to do, I consider my data set, and I am going to, let's say that I give you a bunch of centroids, right? Maybe I start my centroids anywhere, right? Now that you have these centroids, I start with, I'm going to consider a bunch of sets. So I have my data set. These are the samples, the sample bank accounts that I checked, right? And what I do now is that every single of them belongs to one of the clusters, right? Or every couple of them belongs to one cluster. What I do, I start with the first sample and I keep on going. Every time for every sample, I check based on those centroids, I check which centroid is the closest. I'm going to take that one as my cluster, right? That is basically the model that we considered, right? So for every single point inside my data set, I find the k star. K star is the index of the cluster which is closest to the data point xn, and then I say that xn is inside that cluster, right? So what I do, I am getting my whole data set, and now based on the starting random centroids that I started with, I'm going to cluster them into k different clusters, right? Everybody's cool? Everybody sees that? Okay. This is the clustering part. Now, once I'm over, I'm going to look at those clusters that I have made on my data set. And now the next thing is that I want to check whether these centroids that I started with are good choices of centroid or not. So what I do, I start to go inside every single cluster on my data set. It means that I start with the set of the points belonging to the first cluster, C1, for example, right? I write down here if the cluster is not empty, because it might happen that I start with one centroid far away, and none of my data points are close to that one, right? So one cluster could be empty, right? So if it's empty, I cannot do nothing about this. But if the cluster is not empty, what I do, I take my centroid and I shift it to the average point of everybody inside the cluster. Does it make sense to do that? If this is the centroid of a cluster, and there are many points around it in the cluster, those points should be around the centroid, right? This is what the centroid means, right? If all the points are here, if all the points are here, then it doesn't look like some centroid, right? The other sample should have been here, right? So what I do, I'm going to shift this guy to the center of this cluster. Everybody's clear what I'm doing? So I go inside every single cluster, I shift my centroid, so I update my centroid to be the average of the points inside the cluster, right? Meaning that I just average them, I sum them up,